Welcome to today's paper reading. Today's paper is titled, Leave No Context Behind, Efficient Infinite Context Transformers with Infini-attention. This paper introduces an efficient method for scaling transformer-based large language models to infinitely long inputs with bounded memory and computation, published as a preprint by Tsendsuren Munkhdalai and colleagues from Google. This work presents an efficient method for scaling transformer-based large language models, LLMs, to handle infinitely long inputs while maintaining bounded memory and computation requirements. A novel attention technique, called Infini-attention, is introduced. This technique integrates a compressive memory into the standard attention mechanism and combines masked local attention with long-term linear attention within a single transformer block. The effectiveness of this approach is demonstrated through long context language modeling benchmarks, including tasks with sequence lengths of up to 1,500,000 for summarization, using LLMs of sizes 1 billion and 8 billion parameters. The method introduces minimal additional memory parameters and supports fast streaming inference for LLMs. The introduction of this paper highlights the limitations of current transformer models, particularly their quadratic complexity in memory and computation. For instance, a 500B model with a batch size of 512 and context length of 2048 requires a 3 TB memory footprint for KV states. This makes scaling to longer sequences, such as 1M tokens, challenging and costly. To address these issues, the paper proposes the use of compressive memory systems, which maintain a fixed number of parameters to store and recall information efficiently. This approach contrasts with the growing array used in traditional attention mechanisms. The paper introduces a novel attention technique called Infini-attention, which integrates compressive memory into the standard attention mechanism. This allows for the efficient processing of infinitely long inputs with bounded memory and computation resources. Figure 1 illustrates the Infini-attention mechanism, which includes an additional compressive memory integrated with linear attention to handle infinitely long contexts. The figure shows the attention key and value states for the current and previous input segments, labeled as KV-S-1 and KV-S, respectively. Additionally, it highlights the attention queries, denoted as QS, and the position embeddings, labeled as P. Recurrent neural networks, RNNs, process one token at a time, maintaining a fixed size hidden state to represent the entire input sequence. This approach is computationally efficient but struggles with long sequences, as it becomes difficult to store all contextual information in a single vector. To address this, extensions like MetaLearn Neural Memory (MNM) were introduced, which incorporate an external memory component. Unlike RNNs, attention mechanisms do not maintain a recurrent state and perform feed-forward computations on input segments. However, capturing dependencies between segments requires processing them simultaneously, which becomes computationally demanding as sequence length increases. This work aims to improve efficiency while leveraging the expressiveness of attention mechanisms by introducing a recurrent attention layer. Figure 2 illustrates the difference between Infini-transformer and Transformer XL in handling context history. Infini-transformer, shown at the top, retains the entire context history by utilizing a compressive memory, which allows it to maintain and reuse old KV states. On the other hand, Transformer XL, depicted at the bottom, discards old contexts as it only caches the KV states for the last segment processed. This difference in memory management enables Infini-transformer to handle longer sequences more effectively by preserving historical context, while Transformer XL focuses on the most recent segment, potentially losing valuable contextual information from previous segments. The Infini-transformer model is compared with Transformer XL, focusing on its local dot product attention within segments and the introduction of global compressive memory. The Infini-attention mechanism is a recurrent attention process that combines local and global context states. It includes scaled dot product attention and reuses query, key, and value states for efficient memory management. The model maintains a bounded memory footprint while extending the effective context length, enabling long-term context injection through a learned gating scaler. Table 1 compares various transformer models with segment-level memory, detailing their memory size and effective context length. Key parameters include input segment length, n, number of segments, s, number of layers, l, and number of attention heads, h. The memory footprint and context length are crucial for understanding the model's capabilities and handling long sequences. Incremental memory updates are highlighted as a significant feature for efficient long-term context tracking. Figure 3 illustrates the emergence of two types of heads in Infini-attention post-training: specialized heads with gating scores near 0 or 1, and mixer heads with scores close to 0.5. Specialized heads are dedicated to either processing contextual information through local attention mechanisms or retrieving data from compressive memory. Conversely, mixer heads integrate both current contextual information and long-term memory content into a unified output. This dual functionality ensures a balanced approach to handling both immediate and historical data within the Infini-attention framework. In this section, we evaluated our Infini-transformer models on three key benchmarks: long context language modeling, 1M length passkey context block retrieval, and 500K length book summarization tasks. For the language modeling benchmark, the models were trained from scratch, while for the passkey and book summarization tasks, existing LLMs were continually pre-trained to demonstrate the plug-and-play long context adaptation capability of our approach. Implementation details include segment chunking, backpropagation through time, and the use of position embeddings. The results show that the Infini-transformer outperforms other models, achieving a 1:14x compression ratio and improved perplexity scores. Table 2 presents the results of long context language modeling, comparing the average token-level perplexity across different models. The Infini-transformer model demonstrates superior performance over both Transformer XL and memorizing transformers, achieving a significant 1:14x compression ratio. The table also includes a comparison of memory sizes, highlighting the efficiency of the Infini-transformer in managing memory parameters. Table 3 presents the performance of Infini-transformers in solving the passkey task across various context lengths. The task involves retrieving a hidden passkey from long inputs, with lengths ranging from 32K to 1M tokens. The table reports token-level retrieval accuracy, indicating how well the passkey was found when positioned at the start, middle, or end of the input sequence. Notably, Infini-transformers achieve success in this task even after being fine-tuned on inputs of only 5K length, demonstrating their capability to handle extremely long contexts. Table 4 presents the results of book summarization, BookSum, tasks with input lengths up to 500K. The table compares the performance of models like BART, Primera, and Unlimiformer, sourced from Birch et al., 2024. Key metrics include the Rouge overall score, which shows an improvement as the input length increases, indicating better summarization capabilities with larger text inputs. Figure 4 illustrates the performance of Infini-transformers in obtaining better Rouge overall scores as the amount of book text provided as input increases. This demonstrates that Infini-transformers can effectively summarize longer texts, outperforming previous models in the task. The graph clearly shows a trend where more text input leads to higher Rouge scores, indicating improved summarization performance. The related work section discusses several key areas of research. First, compressive memory systems are inspired by the plasticity in biological neurons. These systems use parameterized functions as memory to store and retrieve information, maintaining a constant number of memory parameters for efficiency. Second, compressed input representations summarize past sequence segments, with recent works using transformer LLMs for efficient long context modeling. However, these methods discard old segment memory, limiting their context window. Third, long context continual pre-training extends dot-product attention layers and continues to train LLMs for long context. This includes incorporating sparsity and manipulating position encodings, though these methods face issues like attention sink and lost in the middle when context length exceeds training length. The importance of an effective memory system is highlighted by its role in comprehending long contexts, reasoning, planning, and continual adaptation. This work introduces a novel approach by integrating a compressive memory module into the vanilla dot-product attention layer. This modification allows large language models, LLMs, to process infinitely long contexts with limited memory and computational resources. The approach demonstrates scalability to input sequences of up to 1 million lengths, outperforming existing baselines in long context language modeling and book summarization tasks. Additionally, the method shows a promising capability for length generalization, with a 1 billion parameter model fine-tuned on sequences up to 5,000 lengths successfully solving problems with 1 million length sequences. Thank you for watching.